On 3.2 lesson, I'm going to skip ahead to number 4. They do think that if they tell you you have this, you can write out this dissociation reaction or solubility reaction. It dissociates into the component ions. And if the molar solubility is this, which is not large at all, what is KSP? Well, they told you that the value of S is that. You're going to get one of these and one of those. So the value of S is going to be that. You're going to get the same number for each one. And so K will be this number squared. In 5, we have essentially the opposite. What is the molar solubility if we give you K? So K is unknown. You're supposed to know you get one of these and one of those. So they will be the same number, but we don't know what the number is. We have to square root this number to find the value of S. On number 6, the question is, what's the molar solubility, or in other words, what's S? And they do think you can write out this dissociation equation, or at least recognize we're going to get one of these and two of those, which again sets this up, and we're going to get 4s cubed again. So we have 4s cubed equals the stated value of K divided by 4, cube root that number, and we get S, but the molar solubility is S, but how about the other molarities? Well, this one will be S and this one will be double S. On number 7, we're asked if we would get a precipitate. Well, that will happen when the Q value is too large. They do think you can write out this dissociation reaction, and you are not expected to entirely remember all your common ions, but this would be sulfite. And notice they did give you a giant clue because that's got to be silver, and you have a periodic table just in case you can't remember what silver is, but I'm kind of hoping you can recognize that that's a silver and that's the sulfite. So when these molarities are such that Q is too large, then it can't support this amount of molarity of each, well, at least in that combination, and it will run back to the left and create a solid. So what we're going to do is take the molarity given, multiply by the liters given for that, and divide by the new liters of the combined volumes, or you can do it this way. Knowing that the milliliters will cancel out, you can just multiply by this, and the proportions of 0.05 and 0.1 of course are the same, so you can cheat this way, and we get molarities and we put them in. Remember to square the one for the silver because of the 2 in front of here. We have, and don't double it. Now, the common mistake is to take the molarity and double it, but you know, it's multiplied by 2. That's for when we don't know what the molarity is. If we don't know what the molarity is, we have to say, well, it's double whatever this one is because you get 2 for 1. However, we know what the molarity is. We know for a fact what it is, and it was not provided by the dissociation here. These ions were not created by this dissolving. They were created from something else, and they come from the outside, and they are already dissolved, and we do not know the proportion of them. That's kind of the point. This in no way implies that the molarities we're dealing with right now are in a ratio of 2 to 1 because they did not come from this lump of silver sulfite. They came from some other method from the outside, and they are in God knows what proportion. So this molarity is just a fact, and this molarity is just a fact, and we will take this one and square it. And it turns out Q is greater than K, and so a precipitate forms. Basically, you repeat it for the rest of 7. On the 2006 problem, we have a dissociation reaction already written out for us, a lead value molarity there, a temperature, and liters. And by the way, Kw being 1e negative 14 is only true at 25 degrees Celsius. I don't know if that ever came up in your intro class, but technically that's true. The good news is all our pH type problems are going to be run at that value of temperature, that 25 degrees Celsius, so that's fine. And all this will be true as long as they don't change the temperature, and so we can effectively ignore the temperature. Write the K expression, just remember to square the I. That's about all there is to that. What's the concentration of I? Well, it's just double whatever PB was, wasn't it? So we get molarity of I. Calculate KSP. Now we have PB and I, don't we? And we can just shove them in there and grab the calculator, and we have KSP. For B, a key point to realize is that we have a saturated solution, and that's equilibrium for these kinds of reactions, and therefore K is true. So a saturated solution means as many ions as have been created as it can possibly attain, and if you try to exceed that, then it will run backward and create solid, which is going to come up later. So it settles out so that it's at equilibrium. As many ions are being created as are being destroyed in any given quarter second or whatever time frame you want to pick. And so it's saturated. You can't get any more out of it. So a saturated solution is also at equilibrium, and K is true at that point. And they expect that you know that. I would write that down. Is created by adding the solid, the distilled water, to form 2 liters. You know what? It doesn't matter how many liters. The saturated solution molarity will be true at any given volume, at least as long as you keep 25 degrees Celsius, right? The saturated solution can create only a certain molarity here and a certain molarity there before it starts running backward. So we don't really care in this case what the liters are. The molarities will be true regardless. So we're just going to borrow these numbers from up top. This is the PB, and this is the I, and we're going to say it's the same, but we have to justify it because you can't create any more ion concentration or you'll push Q over K. You want to really throw some knowledge at them, say that Q will exceed K at that point, and that's impossible. Also, the volume does not matter because it's the concentration that matters. And the moles would increase if you had more volume, but not the molarity. Only a certain molarity strength can be achieved no matter what the volume is. In C, they've added solid sodium iodide, but we know that sodium is a supersoluble ion, so this is all going to split up just when it hits water right away. Just give it a tiny bit of a stir. All the ion comes off. Sodium is a supersoluble and desperately tries not to create precipitates, so it effectively disappears from KSP reactions. KSP calculations. So let's just ignore it. Let's talk about the I minus increased. So we increased it, but we increased it in a saturated solution. And as we just said, you can't exceed the saturated solution. It's not possible without changing the temperature, and we didn't change the temperature. Now, by Le Chatelier's principle, if you're going to increase the power of the right side by dosing this whole thing with more of the right side, it's got to run left. So what's got to happen? This is going to react more with the lead ion and create more solid. So the concentration of the lead ion is going to go down and more solid is going to be formed. So what's going to happen? It's going to shift left and create more solid. You might throw that in, and the amount of precipitate will increase, and the lead ion decreases. For D, they have molarities and volumes of certain salts and so forth. But what we're going to talk about is the possibility of forming barium chromate. Now, that's a supersoluble on the nitrate, and that's a supersoluble on the sodium, so the possibility of forming that solid is just at 0, and this is the only possible salt in our double replacement reaction that we should bother considering. So you could figure this out like this and say the molarity times the liters is the moles divided by the new liters is the new molarity, but that's also the same thing as doing this, so there's effectively no difference. So they are correct because the milliliters will cancel out, and it's this multiplying this by the same proportion, so pick a method, it doesn't matter. We get a new molarity for both. Now, will we get a new precipitate? Well, what is Q? Are these molarity values such that Q exceeds K? Do we have too much, or is it at a saturated solution, in which case K is true, or what? So let's take the molarities and put them into our K math, and we get one of these and one of those. So we don't have anything squared. We just have one each, so the concentrations are equal, and they are to the first power each, and so we effectively just multiply these together. Notice they were the same amount. They just did that by coincidence. They just did that because they felt like it. That is not necessarily true. In fact, I was surprised to see that. That is not needed. These could be very different numbers. I can't recall the last time they jury-rigged this so that they're the same. They would not have to be the same because they came from outside sources. So let us not say, oh, they're the same because the ratio is 1-to-1. The ratio is the same because they made them the same because they felt like doing it this time. It is not necessarily the case at all. We take this value times that value, whatever they are, and we get a Q value. It is smaller than K, so we have not exceeded the possible proportion of the molarities, and there is no precipitate formed.